think we're live.
Cool.
Okay, so we're here again streaming Lean. And we've proved a lot of things about lists in the past. Quite a lot of things. And we're going to continue doing that today. I think these all seem pretty hard. So maybe we'll start with one of these drop ones that are easy, just to warm up. And then we'll start taking on these list take functions proofs. If anyone's watching, please say hello in the chat. I'll try to respond. Yeah, today Gregor is with me. Do you want to say hello?
Hello. Yeah, I will join the VS Code hopefully in a moment.
Okay.
Setting this up.
Cool. Yeah, we're trying to pair a program via VS Code Live Share. Okay. Okay, so you're just busy trying to set up the live share.
Yes, I should be able to figure it out in a moment.
Okay, I'm going to start doing these really easy proofs that will be you've done before, basically for take. Okay, the first proof we want to do is say we want to drop 0 elements from a list. If we do that, then that should be equal to the original list. And I think, so I usually look at my previous proofs for hints. I think in this case, like something like sum should work, but we can also do a rewrite from drop, I think. And yeah, that does the job. So yeah, you could also see that GitHub Copilot was telling me how to prove this, which is pretty amazing. Because I don't need to trust GitHub Copilot, I can trust the type checker. So whatever GitHub Copilot gives me, I can just try, because it takes a second, and then if they're wrong, then I can try to prove it properly. Okay, so in this case, this next proof just says, okay, we want to drop some number of elements from a list, but the list itself is the empty list. In that case, we will just get back the empty list. And I think this might not work, but let's see. Yeah. Yeah, so this time GitHub Copilot is wrong. So, and the compiler can tell me. So that's great. I think we might get away with cases on in. We just use GitHub Copilot to give us the syntax here. Oh, okay, well that proves it. So great. I don't even need to understand, but basically by saying 0, it allows me, by doing cases on in, it allows like drop to know which case to take inside the function. And then if it knows that, then we can rewrite with it, basically just doing a calculation of the function in that case. In the case that it takes 0, it will return the empty list. Drop 0, it will return the empty list. In the case that it returns some successor, it will see, oh, the list is empty, so I will return the empty list. I can't drop anything. So it was necessary to take cases, but then Copilot knew how to do the rest. So not that smart, but it's so helpful with syntax. Okay. So in this case, saying drop in +1 of some list with at least one element will then be equal to drop in of x's. Okay, so since it's a +1, there is a successor, which means drop can do some calculation at this stage. And yeah, it can do, and then it will be left with exactly this. So we're done. Gregor, how's your setup coming?
Yes, I managed to join now. Here I am. Can you see my
Okay.
cursor?
Yes, yes. You can type something just to check. Excellent. Okay. Yeah, if anyone's watching, please say hello. Ah, the Mastero. Hello. Thanks for joining. Yeah, please let us know if you have any tips for proofs, or yeah, or just tell us like how you learned about Lean. That'll be interesting. Or how did you find the stream? Either of those, and or both. All right, this is another easy one. Well, easy relative to what we're going to do, not easy. And definitely easy with Copilot helping me. Okay, so let's let's see. Like if we drop, basically if we drop the whole list, then we should be left with the empty list, right? So I think GitHub Copilot was thinking this. I don't think that will work because it can't do it. It can't.
Recursion.
Sorry?
I would say recursion.
Yeah. So what would you say? Like
I would do it with recursion, I think.
so like in cases or induction or
Induction, I mean, yes.
okay, cool. Yeah, but we can't do rewrite because there's no way drop can evaluate one step. So GitHub Copilot is just being naive here. But if we give it a hint, it can at least help us with the syntax, which is amazing. Like, I'll take that every day. And then I can just replace this with sorry, because both don't work. All right, well, in the case x's is null, I would think we can like do some rewrites. Oh, we can use our proof. Oh, that was impressive. Look at that. Like if I figured out, oh, you have this proof, we could just use that. Boom. Ah, I love that. I love that.
That's quite nice.
Yes, because I always forget what I've proved before. Like, oh wow. I don't know if that was lucky or good, but it looked amazing. Okay. How length cons? Do we have this? How does it know? Okay, well let's try it because we have nothing to lose. We don't have to trust it. We can just trust the type checker, right? Yeah, no. Good try. All right. So now, okay, given it entail. If we know this, oh, here we go. Okay, yeah, we look on the right side. Sorry, I forgot. I got GitHub Copilot was doing so much for me. I forgot to look at the state of the proof.
Yeah,
Okay.
can we pull out the head there somehow?
Yes, I think we can rewrite length because it can look at the head, right? And then you can say this is 1 plus length of tail. And that means the drop can take a step forward as well and pull out the head here. So if we say rewrite with length, that'll give us the +1, and then drop can calculate because it can see the.
Oh yeah.
Okay, and yeah, that's our induction hypothesis. So that's, I think we can use assumption for a change, or the other option is to use exact induction hypothesis. Okay. Oh, Lamastero 2 says yes. I'm new to Lean. Just tried number game. Cool. I've not heard of the number game. That sounds great. Yeah, paste the link in the chat. Okay. Yeah. But yeah, feel free to chat as much as you want. Like, but no pressure to post if you don't want to. You're welcome to just watch. Oh, there's the game. Okay. Whoa, look at this. Okay. So Limastero 2 sent us this.
I'll quickly open the Twitch. I don't even have it open.
Oh, and then you can do Lean inside the browser. Oh, okay. Okay. Oh, and then you can just like say, okay, maybe this is sump. You do. Oh, wow. Okay. Okay. That a thing? It's not add a thing. Oh, I forgot. Zero add. What's the function name for add? Oh, okay. I see. I see. We have to use these theorems. Okay. Or we're going to write them. Oh, okay. This is the tactics that we are supposed to use. Okay. Yeah. Cool. Yeah. So we can definitely do this with induction, but like, oh, and then it's, wow. Okay. That's really cool. Wow. 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 Oh, look at this. It's on the side as well. Okay, that's, then we can go back here and we can follow this tree of how we're going to learn things.
I can only see your VS Code in your shared screen.
Oh,
Yeah.
oh,
I on the Twitch as well.
oh, that sucks. Okay. Okay, sorry, but okay, why is that? Okay, just give me a second. This one. Okay, here we go. Here we go again. There we go. Okay.
Yes, perfect.
Okay. So yeah, there's this number game, and it teaches you Lean, and you start like from addition, and it shows you, okay, this is the theorems we want, this is the tactics we're going to use. It's also here on the side to make it like easy for you to like reference and read about.
Oh wow, this is so cool.
This is really cool. And then you can try to prove it in the browser, which I've just failed to do, but like it's been a while since I've practiced. And this doesn't have GitHub Copilot, so I'm pretty useless now. Like but then you have this tree that you can follow to learn more and use more and more tactics as you go along. This is yeah, very cool. Very cool. Oh, yeah, even T auto and have, that's good. And symmetry. Oh, symmetry. We struggled to find that for a while at some stage. I wonder if this is a Lean 3 or 4. Yeah, I don't know. Okay, don't know. This might be Lean 3, I'm not sure. But still really, really cool.
Maybe in the FAQs it says so. That yeah.
Oh, Google for 3. Safari. No, there's no mention here. But yeah, it's really cool either way. Thanks for sending this. Well, okay, but let's go back to our proofs. I think maybe this is the last one before we go to the harder proofs.
Okay, so I suspect it's again something with the predecessor. The less or equal ones were always with the predecessor function.
Yeah. Yeah. Okay, but first we want to do induction on n or x's, and we probably want to revert the other one. Just gonna guess, but
I would say induction on n.
yeah, let's start with that.
Because n is on the right hand side of the less or equal. Then the length must be 0. That's just my intuition.
Sorry. Yeah, okay, here we go.
Oh, maybe suck n prime. Otherwise, we have 2 n's.
No, it overrides the previous one.
Oh, okay.
Yeah. So I was also doing this before, and then so if we go here, right? There's no n.
Oh, okay.
Yeah. So then it's just like, okay, I don't want to type prime for no reason.
Yeah, it's strange though that there is no n anymore. Well, oh, it makes sense because we do induction on n. So,
Yes.
Yeah.
Exactly.
N is literally the successor of whatever we name it. Yeah.
Yes. Yeah. So it's like just okay, let's just keep it simple. But yeah. Well, it depends on yeah, who you ask. Like I think that'll be a contentious point. Okay. Okay, if the length is less than 0, this should be, then it must be the empty list. So, but also drop 0 will be the empty. Well, no, it won't. Okay.
Yeah,
But,
isn't there like maybe a theorem
intro
in
this.
the library if the length is smaller than 0, or do we have something like that already? Maybe
That would be good.
list length.
Yeah.
List. No, we have some that start with list length. Oh, list length 0 or smaller is empty. Yeah, that's the name of the theorem.
Okay. List.
Line 198.
Yeah, 100. That'll be easier.
I could just have typed it. I always forget.
Okay.
uh,
Yeah, that's good. That's good. That's exactly what we want. Okay, well, let me just hold it on the screen for a second. But yeah, we want to say, yeah, if the length is less than or equal to 0, then the list is equal to 0. Where were we? Well, I forgot. Okay, here we are. Okay, sorry about that. So we want to apply this to
H.
Yeah. Can we? I forget. I know you can do this in Coq, but
That's also something I'm very confused about. I think you can't apply something to hypotheses.
Yeah, so you have to
I was always doing it with this have thing.
Yeah. No, I think you can get away without the. So yeah, okay, we just need to do that. Okay. So have empty list, and then we can rewrite with empty list. And then we should just be able to rewrite with drop. Yeah, there we go. Cool. So now we want to prove this.
And I think that's where the predecessor comes in, the pred function.
Okay, the pred function they're saying.
We have some nice theorems about pred.
Yeah, I don't think we need pred. We're gonna need suck, right? I think they use this.
Yeah, I was also looking at that one. Yeah.
Okay, but okay, we'll come back to that. We first need to get stuck. I think for that we need to take cases on X so that we can move this drop on 1. Then we can drop something. No. And cons X is no induction hypothesis. I'm just guessing we won't need it. Okay. Okay. I think we can rewrite with length at least. It's a good 0 smaller than successor of n, which is pretty useless information. But yeah,
we can probably rewrite that as just as true, and then we can just discard it.
Yeah,
or we can just intro
it and ignore it.
Yeah, true.
And now, yeah, we can rewrite with drop because it can take on 1, and then we're done. Yeah, because yeah, it's just trying to prove it's equal to the empty list.
Oh yeah.
And if it tries to take the successor of, like, it's trying to drop something, it seizes the empty list, then it just short circuits. So that does that for us. Okay. Okay, well, this is a freebie, so I'll take it. Can I also add there? Can I do that? Yes. Okay. So I just rewrote with the length here so that it got the +1 out.
Maybe you can rewrite it to have suck on both sides. Does that help us at all?
We'll see, but like I think we can at least calculate drop for both of these. No, we can only calculate drop down here. And then we might as well intro it. Okay, so if we know that, no, this doesn't help us, right? Because if something is bigger, we're just adding 1, but yeah, so it won't help us get this. Huh. That did not go as planned.
But the list we are working on in the induction hypothesis is 1 longer. So
Yeah. Yeah, so I'm not happy where we are. Oh, okay. Let's go back. I want to revert X's here. Just taking a shot. And then intro X's here. Then, okay. So things just changed a bit because our induction hypothesis now allows us to put in a list. And this also looks better. Oh no, it looks the same. It looks the same. But we can intro it. We can probably remove. It would be nice to remove the one on both sides, the +1.
Yeah, that's what we have this one theorem for.
Yeah.
I think I have something. This let me check.
Yeah, we don't have a lot of net theorems, but they should be in the library. Oh yeah, and we do need it. We do need it because we're going to use it up here in the induction hypothesis. And then, yeah, after drop and calculate one step, it should be what we need. I'm just going to do that part. Yeah. So we just need to prove this, and then we get this, and we're done.
We can remove it on. No, that's slightly different.
I might. Well, we can just write a quick theorem for it.
Yeah.
It's not ideal, but
I only see in line 307. I have theorem. Yeah, it's a bit different, but yeah, I think we need to use like some pattern matching for it because it's this strange problem with the pred function. Was not able to prove it without the pattern matching, so we could use this as a template of sorts.
Just okay. Sorry. I was just concentrating on too many things. Can you just repeat? I'm sorry.
I'm just saying that which line are you? Are there? I think we have to use like some kind of pattern matching for that theorem because it's this strange problem with the pred function. But let's see.
Well, we can apply suck and net suck.
Oh, right. Okay, that's nice.
Yeah. Whoa! What did you just do?
Oh, oops.
Redo.
Redo. Wait. Redo. Oh. Sorry.
Yeah. Okay. Cool. Better. I think we're fine. Okay. So I just need to. I think what will also be better is just to say X and Y, X, Y. Because yeah, we don't need to care about lists for this theorem. And then yeah, we need to split because is that a thing? Oh. How do we is the tactical split in this language as well in LeanProver?
I don't think so.
Let's go see.
Well, there is a split thing, but let's check. Where's the
Here's all the tactics. The web page with all the tactics for me. Let's zoom in a bit. Other ideas, just search for this, but I'll probably use the Unicode. Where are we? There. Let's see if we find this character. Yeah. If and only if intro. I remember something like this. Oh. I think here it is breaking it apart. Yeah, these okay. We might have some examples in this file. Yeah, apply if and only if intro. There we go. So should be able to do that. Okay. Case MP, case MPR. Yeah. All right. Okay. There we go. Now we can start. Okay, so you wanted to take cases on induction on X.
No, can't we just apply the cyclist rule? Yeah.
Okay. Yes.
Yeah.
Okay. Okay, I'm just going to take a chance. Yeah, that worked. Okay. All right. So basically, these were our theorems.
Perfect.
Yes. Okay, so that's another way to find theorems is write them out and then let GitHub Copilot try to prove them for you. It might just reference the theorem that already exists.
It's pretty good at guessing the names.
Yeah, it's really, really
or
good.
interpreting the names if you write a good name.
Yes. Okay, so maybe like, yeah, I don't know if we should have this theorem, but I'm gonna call this net suck if only if.
I think it will come in pretty handy.
Yeah. Yeah.
Yeah, I mean, not only for this proof, probably also for other ones.
All right, so then we should be able to rewrite. Oh, yeah. Okay. Well, it already knows what we want to do. All right, but I want to use ours now. I'm sorry. We spent all this time. Okay, so why not?
It's not even working. Does it not take any?
Oh, we have to say
Hmm.
length x's and in. No? Okay, what's the problem? Function expected at RMS type. You see, and Cock it would guess which way to go.
Hmm.
And here,
The type, it says, oh, and maybe the other way around. First, no.
no. Okay, but we can say,
Okay.
I think this can be inferred at least.
My info view is just giving me nonsense information again. Should look at your screen.
Oh, sorry.
Hmm.
So okay, fine.
Well, maybe yeah, maybe let's use the existing rule.
Okay, and then yeah, this looks right. But basically, we just have to go. The induction hypothesis requires this h prime to be passed to it, and then it will return this, which is exactly the goal. So, okay, what did you say? There we go. Boom. All right, now let's go back to the. Oh, we got just.
No, we need H. Because
No, no, no.
we introduce it there. Yeah.
Then. Oh, I just wanted to remove a few h's here. Okay. Then I can use the warnings to help me find where we are. Okay. This is, yeah, it already wants to revert anyway. This is a
Probably
pretty,
because we used revert so often in the last theorems.
yeah, but this proof just is going to be pretty involved. So we might need all the generalizations we can take, we can get, but I don't know if we actually want to do induction on n first and rather revert x's and y's. See.
Oh, you can revert two at a time. That's nice.
Yeah. Okay. Okay, so that's great. We still have the generalization here because oh, weird. Okay. Anyway, let's start.
Well,
we can
rewrite, I would say.
Okay. No. Okay. 0 minus length.
We can probably use the theorem if the length is smaller or equal to something, like list take length.
Well, I think like subtracting anything from 0 is 0. Because it's
Oh,
a natural.
yes, yeah, probably, yeah, we can rewrite that, and then we can list take 0. There's a theorem, I think.
So I don't know what the
List
theorem.
take 0. It's called line 276.
Yeah, but we first need to prove that it's 0, right?
Isn't that just application of or like rewriting this subtraction?
Yeah, do you know what the function name is?
No.
Same here. So I'm gonna try it. Let's use that trick we had before, right? So 0 minus x equals 0. Let's see. Oh, really? It can't find it for us. Like,
Isn't it maybe like net dot tab or net?
sub 0. What is net sub 0? No, that's the reverse. We want 0 sub. Maybe we're lucky. Yes, I found it with my roundabout way.
Yeah,
I hate
luckily
it.
the things have to have proper names.
Yeah, yeah. That sucked. That sucked. Okay. And now we can rewrite the take again. I don't know if there's a rewrite star or something.
No, repeat, I think it's called. Repeat.
Yeah, there we go. There we
Yeah.
go. All right, yeah. So we rewrite the sub, and then we can rewrite with take, and end up with this. And then I think you said something about the pained null.
There was no, we had list take. No, so if you would rewrite only once with take, we could use our previous theorem.
We just need this, right?
Yeah, well, probably we can rewrite with just append.
Yeah.
I suppose. Is it maybe H append or something like that? I don't know why it was. I saw H with capital H, I think.
We can also do sump. I think it's fine now.
Yeah.
Oh, okay, but I do, yeah, like this.
Yeah, happened.
No, didn't work. Sorry. Good idea. I think I know where you're going. I think that was the right place to go. Oh wow, look at this. Look at Git Copilot things we can do. And
Yeah, looks like a good suggestion.
go on. Like, why did it stop? No, sorry. Oh no, two mistakes. Okay, well, you tried. We'll take over from here.
Like, where does this come from?
But was there a reject button somewhere? No, you can only accept it. Okay. Okay, so we have a nice generalized induction hypothesis. That's great. But now I think we can intro. Well, we're probably going to do cases on X's, I think. So this looks about right. Yeah, cool. We got lucky. This is apparently correct. I think this should also work. No.
We could certainly use repeat rather than all these rewrite takes.
And then was this necessary? No, it didn't do anything. No, it didn't do anything. Yeah, that's the proof.
Essence of it.
Cool. Oh, it's just now. Oh, no, I can do better. I promise. I can do better. No, no, you can't. Okay, that was a good shot. Okay. Well, this is long. It's like this is equal to this.
Yeah, I have to pause that
Yeah.
in my head.
I think I can do repeat, rewrite take. That will do something. No? Why not?
Oh, strange.
If you take, yeah, you should be taking this. Why aren't you calculating this? Because is this binding stronger? Oh, that would be irritating. Okay,
No,
let's just
there
do
was a
one at a time.
theorem that looked very much like that.
Okay, this simplified something. What did it simplify? Oh, with Coq, you can like see this whole difference between the first line and the previous line, and that's really, really helpful.
Oh yeah, I turned on all the diff options in my Coq IDE.
Yeah, makes it's much nicer. Okay, but this is the one that gets rewritten. See, there's the head taken out.
Yeah.
So here, suck in minus length h tail, right? I think some of this should be able to be calculated. So we can at least do rewrite length. Yeah. So now if you have +1 on the one side of the minus and +1 on the other side of the minus, I'm hoping they can do something. No? No. What did they simplify?
I had a theorem relating,
Oh,
but it was
I pushed all these things together with the no. Okay, I want to simplify this to just be n minus length tail, because then it looks like that. Does that make sense? And we can make this x and x's.
I think we can. I think the easiest would probably be to have a small theorem as a rewrite rule, where we just have this is equal to n minus length x's.
I agree.
Because we can just do the what is it, the conquer arc thing with equality and just add. No, we don't even have to. Probably could just simplify.
I think we should just be able to rewrite.
Yeah.
And I think we might be able to get away with this just being y, this being x, and maybe this is just suck.
Yeah, it looks much nicer.
So nat suck means suck sub suck. And oh, look at that. It guesses the theorem from the name.
Oh, and it does it correctly. Nice.
Yeah, it looks better than what I wrote, so I'm just gonna delete that.
Yeah, that's the one thing GitHub Copilot is good in with Lean, guessing the theorems from the names.
It's so good. Okay, but it's not good at this. Whoa, 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 whoa. Okay. Yeah, I think, well, I think we have to do induction on in. So if n is 0, can we do the sum? No. Huh. 1 minus. I think that's true. Oh, no, it is true. It is true.
Yeah, sec m is definitely greater than or equal to 1.
Yeah, but why couldn't sump do just a little thing for us? Okay, let's. Come on, sump. Like, net dot sub. Can we? Is that maybe the? Yeah, but these, one of these is correct. Is one of the theorems we want.
Would be just nice to know what where are the natural numbers defined. Let's check. Go to definition.
Yeah, no, doesn't work. Oh wait, there we go.
Subtraction. Net dot sub.
Yeah.
Net dot sub is subtraction.
Yeah, that's what I tried before. Well, the brute force isn't that bad. Just to do cases in. No, it doesn't really help. Wow, 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 wow. No, is this gonna be one of those things like last time?
Oh no, please not.
Where you get stuck. Okay. You know what? That's a nice proof for later. Okay. Pretty
Let's
sure.
skip this one for now before we get frustrated.
Yeah. Yeah. That's one exercise for the watcher. The watchers. Or we'll tackle it later. Team. Yeah. So simple and so hard. Okay. Now we can rewrite with it, with our theorem that we haven't proved. And boom, it worked. So we removed our second +1 that we wanted to remove. Okay, now I want this to tick along and bring this x outside so that we have it on both sides. And then we should have exactly this theorem that we have here with x's at the front. So this should be I don't know why it's not proofed by default, but let's see. Maybe we have some. Do we have any take proofs already that might tackle this?
We have, oh, but this is exactly, oh no. I think we have one that is like sort of the opposite.
Yeah, let's take cons.
This take cons.
Yeah, it should just be rewrite take, but
doesn't the cons thing bind stronger than append?
yeah, apparently, yes. So let's have ourselves a little theorem. I want to say let's take cons append.
No, that's not the theorem.
It's close. It's close. So that just means I named it wrong, right?
Yeah, I guess so.
Yeah, no, this is what we're trying to prove down here. It's trying to like, no. Okay. Yeah. Gonna try again. No. Sorry, buddy. All right, but it is this part. And then we say it's equal to this. Like so. And all of these should be implied because kind of obvious. Okay. Okay. Then let's just check whether this would work first. So we use our proof, rewrite with this, and now we have x's at the front. And now we should be able to use conger arg with just removing the head from the list on both sides. This should be here, and head is x. Yeah, so that removes the x from the front. And if we look at that, it should be exactly, it's exactly the same, except list append is written out for some reason. So we should just be able to say apply IH. And we're done. So now we can go concentrate on this. I think we can do this one. Oh, Lamastero needs to go. Oh, thank you so much. Yeah, like he says, yeah, great idea to stream on Twitch. Thank you so much for watching. It's great to have you. Please come again.
Cheers.
Okay, I might have missed him already. I don't know when he typed it or they typed it. Okay. Let's see.
Maybe we have some nice theorem to rewrite what is in the brackets there.
Yes. Yeah, we kind of want to say theorem this equals this, right?
Like there was something. Yeah, here is theorem list app com cons in line 72.
Yes. Nice. Okay, so we should be able to maybe instead of this do this. No, we're not that lucky. Okay, let's try it here first. No?
Maybe the reverse, maybe the backwards arrow before.
Do we put it here? I can't remember.
No, not there. Inside the
Inside.
brackets. Yeah.
Hey. Okay. So let's try this here, and then after doing that, we should be able to rewrite with take. I think we could just do. Oh, okay. We don't even need to. But let's just do it for. Yes. No. Yeah, that worked. Okay. Cool. Okay, now we can delete. This is not necessary. All right. I'm really gonna leave this. I'm really not gonna do it.
Yeah.
That was a good one. Do we want to take like a 5-minute break?
Yeah, sure.
Cool. I'll see you here again in 5 minutes or
Okay,
about that time.
cool. See you in a moment.
Cool. Bye. Hey.
Hello. Yeah, I tried to figure out this suck sub suck, but no chance.
Yeah. So I think it comes down to this basic thing that I don't know how to rewrite on symbols. And I think it's because it goes through these instances, and there's just something that like we don't know how to do there yet. But if we had that, then it would be much simpler. And it's just one trick we need to learn that we don't know yet. But I don't want to try to do that now. Like let's continue doing the proofs we know how to do, and when we figure that out, we can start using that trick on the stream.
Yes. Yeah, I didn't want to suggest to do it now. It would just be interesting to find out how this
No, we
pattern
have
gets.
to. We have to at some point. Like there's no dodging it. It's just not right now. Like all right, so what's this one about? It says take some length plus in. That means taking the whole of x plus some of y. Okay, that makes sense. Let's see. I think maybe doing induction on x's first, since it's the first thing mentioned.
Didn't we have a theorem already that allows us to take like things apart with take? If we have take x, take n plus m or something. I mean, I think there is a theorem like this, but I'm not sure whether it is further down or whether we have already done it.
I'm looking, yeah, not sure. No, I don't think so. I think this is the, but yeah, like if you find it, like I want to start with induction on x's and see where we get. Okay. Okay, that's it. Okay. Lucky. But just to be clear, like look at this. The length is 0, so it's take in of y's equals take in of y's. So it is very like simple. That's where we want to get with all these list proofs. Once we've completed them, we want to pull them into a library where we just go, oh, it's something with lists, just figure it out.
Yeah, that would be nice.
That's why we're building this library. But yeah, it's not that simple to just put it in a library. It's a whole process as well. Because you don't want to go in circles, and you always want to move forward and things like this. So you just want to use in this library what will always take you forward. So and then you want to have some other tactic that's a bit more aggressive and tries more things than just the simple things. So it's, yeah, a balance.
Yeah, I think I've read something in the tutorial that you can so of course you can mark like theorems to be recognized by sim, but then also you can do that only like conditionally or something, or only if you, I mean, you don't always want all your theorems in the global sim.
Yeah, yeah.
Um,
I think it's simp only. And then
oh yeah, I think
you
that was it.
only this, yeah. Yeah, that's very useful. Okay, in this case, so you can see here at the top, like the induction hypothesis is already kind of here, right? It just says this X is in front on the right side of the equality. So if we can get the left side of the equality to look the same, then we're done. And this should be possible, because this should be a suck, end up being a suck length x's plus n. And this should end up being, well, ready for the taking. We might need to use list app cons again. So maybe we'll even start with that. Yeah, cool. So this one has been rewritten, ready for us. And so we can like rewrite with length to get the +1 we need. Oh, that's irritating. I hope it's okay. Let's rewrite with take and see if it works. No, we're unlucky. We want this, the one to be on the other side.
Isn't there like a commutativity thing that we can just apply?
Yeah, there has to be. Add com. Oh no. That maybe the other way. No, somehow that's worse.
Hmm.
Okay, okay. So this is where have, I think, comes really it comes really handy. Equals, yeah. Can we do this? Yeah, and then okay, so that will work. We just need, I think, did it work? No. Like, okay. Sorry, let me just. All right, we have this, and we want this. We've proved it. Then we rewrite. And that thing we write. Oh, there we go.
Yeah.
Oh, we want this actually. Yeah, there we go. I think actually we want that. No? Okay. Let me just give it what it wants. Okay, here we go. We want to prove that. Then we can take, and we should have the x's up front. We can do the Conger arc thing and apply the induction hypothesis.
I think we probably first have to use associativity and then commutativity. Or something like that. Rewrite with net assoc or something.
That's a good one. Yes. Yeah, that's good. I kind of want to rewrite with net assoc again here now. Will it let me? No. Okay.
No, but now with commutativity, and then
I think we're done. Are we done? No. Okay, what did we do? Let's just
yeah, what did it swap?
so we put it there, and now
Then, oh no, it swaps these. No, but it should swap the thing inside. Oh, oh no. Like in Coq, you can specify that.
Oh, wait,
I think.
it was saying something here. Yeah, you can provide the arguments.
Oh, okay.
So we wanted.
Oh, nice. Yeah. And now we can use SOC again.
Oh, so here, I think, what did we give S up here by?
Oh, and so actually that looks like the one that we actually want to have. So in the theorem, so we don't want to have suc length plus 1 on the right hand side, but length x is plus n and then plus 1 at the end.
We do need the successor here.
Do we?
Yeah, yeah.
Well.
Yeah. Yeah.
Oh no, so then we first have to use the commutativity. I think.
Yeah, just yeah, okay. Let's try it.
And just but not on 1 and n, but on the other one on length xs and 1.
Okay.
And then
Oh, now we want to use the. Now we just want to swap.
so now it's just commutativity again.
Yeah, but not with these.
And that's just now.
Why is that not again?
Can't we do just sim now and we're done?
Yeah. Yeah, let's see.
No.
Yeah. I feel like
Oh no, isn't it like reflexivity? Or maybe rewrite with.
There we go. There it is.
Oh yeah. Cool.
Okay, there has to be a tactic for this. Like I'm sure. Like Coq has one. It's just called Leah. And it just does. Okay. You have some math thing that needs swapping around, just do Leah. Like LIA. It's just great.
LIA. Okay.
Yeah.
What does that stand for?
I can't remember. Just yeah, you have to use it. Just avoid things like this. To avoid exactly this. Like you just don't want to waste your time on that. All right. Well, we're making good progress, so let's continue. Okay, here I want to take something twice. Then it's like taking the minimum of
Take it. Oh yeah, it makes sense. It takes m and then it takes n. So whatever is smaller, that is. taken in total? If we have a list with 100 elements and we take 50 and then 10, we have 10, or if we take 10 and then 50, we also have 10.
Yes. Wow. Okay. Yeah. That's.
That looks tricky.
This looks very tricky. Pretty sure we're not going to use this in the long run, but yeah, might be a good one to end with. Like, let's see how far we can get in like half an hour. And
Yeah, a good one to get stuck on with.
yeah, I think this one might be worth getting stuck on. I don't want to get stuck on. What was that one?
The suck.
Yeah, this one. No, I don't want to waste time there. But like this one, we haven't worked with many yet. Might be interesting.
Yeah, we don't have to feel too bad. We
Yeah.
get stuck here.
It'll be slightly less embarrassing. Yeah. Okay. Well, I'm gonna revert everything I can here, and I think we can start with induction on N. Because that's, I don't know. I always like to start with induction on the first thing that's mentioned. So we'll revert X's and M. Yeah, should have nothing. And then we can say, yeah, induction in. I don't trust you to figure this one out. But it doesn't, no, yeah, I knew it. Doesn't cost me anything, but still, whenever the proof is long, it's probably not great. Okay. This is not, it's suck in IH. Okay. And whoa. Okay. Oh, yeah, I'm pretty sure we're gonna have to do induction or cases on M. I can't. And
so min 0 M, we can definitely rewrite this.
Okay, that's a good point.
Maybe backwards, rewrite backwards.
Let's go look at min.
Yeah.
Oh, okay. This is
what is that?
great. Okay, so saying define min. So this is the, I assume the less than or equal. Yes, so this type class supports less than or equal. And then we have another type class here. It says something is, it's a decidable relation. It's saying less than or equal, but that less than or equal has to be a decidable relation.
I suppose that's something like a linear order, total order. So every two elements are comparable.
Yeah,
probably.
Yeah, basically everything will return a value. They won't get stuck, like trying to compare with each other. Like there's a recursive loop there. It will end. So basically it's the less than or equal that we're used to. And then it says
if then else. Oh, if then else. Okay. Oh, that's straightforward.
Okay, so if A is less than or equal to B, oh, then return A, otherwise return B. Okay.
Okay. Nice.
We can't.
But I've never worked with if then else before.
Yeah, but that means we can't like use no, it's
but cases probably. We can probably use
like it's just a function. Oh, cases on like
okay. Oh yeah.
So much more complicated than it. Wow, okay. Anyway, where were we? So the problem is that less than or equal to evaluate needs both A and B, like to evaluate.
But it shouldn't be too hard to prove a little theorem that the min of 0 and anything else will always be 0.
Yeah, let's do that. Let's do that. That's, yeah. Well, we say it shouldn't be too hard, but no. I can't see what I want to prove. Wait a second. Like this, okay. Yeah. And let's call it net min 0. Yeah, okay, fine. Okay,
Nice.
so what did this do? Okay, it rewrite with min. Then it gave us it unfurled, what do you call it? Unfolded. Yeah, can we do unfold so? Yeah, unfolded the if then else, so we can actually read it. And then you check this, and this was always true because of sump. Okay, well, fine.
Backwards.
No. Okay, we'll give it.
Oh, it takes a parameter.
Yeah. Yeah, m. What's wrong with m?
Or maybe you can make the n implicit in the theorem.
Yeah, okay, let's. Oh, I think we first have to intro. That's the problem. Yeah, there we go. And take 0, we can. That works.
Yes, and there as well.
Yeah, we're done.
Nice.
Okay. That's good. Yeah, I'm pretty sure that's not correct. I do think now. We do need to do maybe induction on m. I don't think we're gonna get away without going deeper. I don't know if we'll need the induction. We can come and delete it later if we don't, but if we just need cases, then it's fine. But okay.
Why is it not happy?
Yeah, that's weird. Why is it not happy? I think maybe not this.
Don't you have to intro m first?
Yep. Well, and yeah, m is net. Good. Yes. Okay. Good catch. Oh, this one can go away, at least.
And then we have another min suck 0. It's just the other way around. So we have to. We should maybe have a theorem not 0 min as well.
Yeah. Yeah. Cool. Cool. That works.
But the theorem is the same. So.
Thought that was too easy. Okay. Now we have to do cases on X. Yeah. And yeah, maybe we can do this. Okay. I think we can. Here's maybe a nice theorem. No, we don't need type.
Yeah.
So
Is the successor of min nm.
Yes. What do you think? I think that'll be useful.
Yes, that looks good.
Men
Suck min suck.
men suck, yes. I love that it's like Lean can infer all these variables, and I don't like.
That is very convenient. Yeah.
Like it's nice to go and add them later, but if you just want to like make progress, it's really nice that they're just inferred. Because in Coq you have to always go, okay, like I have some type, and then I have a list of that. It's like, no, just if I have a list of that, obviously I have some type for it. Like, yeah, so you can just almost type like you type Haskell, and
Oh yeah.
and you just by chance have dependent types. Okay, now how are we going to do this? This is a very nice one. Well, I think we start with this as always. We can just repeat that everywhere. Thanks. Okay.
Then cases probably
Um,
on. Yeah, I mean, so if the success of n is smaller than the success of m, then n is smaller than m. So we can use
okay.
suckless suck there. If we have.
Okay, so you're saying
Can't we do like, can't we break up the like an if else thing in the two cases, if that is true and if that is false or something like that?
I don't understand.
So I mean, either we have that the statement suck 0 less than or equals suck m is true, or it's false. So I thought maybe we can do cases on that somehow. So we would have that as a hypothesis, and then that
We
is
can.
false as a
But it-
hypothesis in the other
But
case.
it might be better to do it on like n smaller or equal to m, and then we prove that like they'll also be the same here. So just
Yeah,
instead of the suck, we do this.
yeah.
I wasn't sure what it was, if it was going to be true or like what was the syntax going to be. Okay, but it's not working. It's not working. Maybe no, they are introduced. Do I have?
I mean, can we do it like this? Even?
Well, in cock,
Cock?
but otherwise we can go have cond. Can we do
But
that?
we would need to prove that, don't we?
And then,
If we have.
oh yeah, it's a. Mm, hmm. Yeah, because you want to say this is a bool. Oh, it is this type. Mm,
But we can't prove it because we don't know.
yes.
Mm.
Late? That a thing? Yeah. And then, yeah, we can't do cases on that. If it's decidable, right, then you can assign it to a Boolean instead of a prop. So in general, if you use this, then that.
But maybe maybe cases is just not the right tactic. Maybe there's something to break up this if else thing into sub goals.
Okay, yeah, yeah.
I'll quickly search for that. Break if else. There's also by cases. What's the difference between cases and by cases?
I can you type it?
Yeah, it's where were we?
Type it up here at 406.
406.
407.
There we go. By cases. What does this do? My info view is not working.
Oh yeah, it splits the main goal into two cases.
Oh, nice.
So what do we actually have to type? Can you just type by cases? And then
So what are the prop true? So
I'm gonna hope not. But I think you were on to this if then else. Like there has to be.
The other goals are just both the same. Oh, it's probably because it's an equality and not just. No. Hmm.
Here's some if then else proofs, but they're not very useful. I wonder before we rewrite with min, maybe this is
Where we can use by cases.
no, I don't think it's gonna work for us. So we don't want to talk about prop. We
No.
want to use the fact that this is decidable. And rewrite min goes kind of too far. Because now we're at the if, but we really want to be at the if then else, the ITE, which remembers that it is decidable. So but we do need to unfold. Yeah. It unfolds too far.
Maybe if we rewrite now backwards with ITE or something like that.
Yeah.
Decidable cases on.
Hey, what? Wow, okay.
That looks interesting. So maybe we can now do cases.
Okay. No.
No, but I mean normal cases.
Oh.
And then I'm not sure what it would do cases on.
Yeah, we want to do cases, decla, nm. Yeah. No. Okay, declas. So this is decidable less than or equal, right? Oh, there. Blee. Boolean less than or equal. That's there we go.
Oh wow. Okay.
Let's just see what we get.
Do we need the rewrite ITE at all? Maybe it was the mistake was just that we did not use the BLE.
Yeah. Yeah. Okay, but problem here is like it's forgotten. So it needs to remember like this is an hypothesis and then go, okay. So there is something for this. And I think Lean has a nice way of doing that. And like with cases where it gives it a name. Where in Coq we would always write remember this and then go cases.
Hmm.
I'm just wondering, maybe we did something like that here before. But I don't think so. Maybe it was in one of the other files.
Or maybe we can try the let thing. We let some variable be equal to that, and then we do cases on that.
Yeah, yeah. Yeah, worst case that will work. That's a good idea. We were here, right? So late cond. And then do this. Why aren't you remembering that it's true? Maybe on equal. Is this a thing? Okay, how about this? Also, yeah, we've done okay. Yeah, and this was just unfoldment, actually. Prefer that. Okay. Wow. There's definitely an easier way to do this.
Yeah, there must be.
But yeah. I think we should call it a day.
Yeah, maybe.
This was
This is a good place to get stuck.
yes, exactly. So I'm gonna leave that there. I'm just gonna see. Just gonna try and leave this code in a good place. What were we trying? Yeah, no, we don't know if this would have helped. So I'm gonna actually remove this. And I'm also gonna delete all of this. Yeah, I think just leave the parts that are definitely useful.
But we did some theorems.
Yes, we did a lot. That was a really good run. And yeah, that meant that if then else is pretty interesting. And yeah, after that, figure that one out. These all look. Oh, the split is going to be interesting. And
probably a cases thing. I know it's and
yeah, there's still a few interesting ones. Like, oh, there's exists. Nice. Okay, so we still have a few things to learn in this file, and then yeah, we'll have a good library of how to prove things as well. Especially, yeah, there's a few things we need to follow up on, like this net sub suck sub, and also understanding why we can't prove this with a tactic.
And understanding how to do this in this way.
Yeah, that too. Actually, yeah, that might be better. Yeah. So yeah, still a few things to learn, but we're getting somewhere. We're getting somewhere slowly. Cool. Well, yeah, I'm gonna stop the stream. So yeah, thanks everyone for joining and watching. And yeah, have a good rest of your day.
Yeah, have a good evening. Cheers.